Now we're going to talk about some of the concepts in concurrency, such as atomicity, mutual exclusion, and how those are obtained, for example, using locks, right? So the basic idea is that you have different variables, you have different variables, let's say x is 1 and then y is 2. And what you'd like to do is you would like to change them together to some different values at the same time. So you want both of these variables to move from this state to this state without anybody else being able to see that, oh, x changes first and then y changes, right? And like the whole reason all of this really comes up is because there may be multiple threads that are executing in the system, right? So let's say you are doing this, you are changing this on thread 1, right? You are changing x and y on thread 1, and then thread 2 of course has access to these variables at the same time. So thread 1 executes x equals 2, and then thread 2, if it reads these values at this point of time, what it will see is x has changed to 2, but then y is still 2. Right? So now it sees that there is an intermediate state where which we didn't want y to see, where x is 2 and y is 2. And let's say assume what we always want to maintain was y is always bigger than 2. Right? So let's say that's the correctness criteria we wanted. And if we atomically updated both, like x and y are together updated, we still maintain this property, right? But here we see that thread 2 sees x equals 2 and y equals 2 at the same time. So it sees this sort of like invalid state that we don't want it to see, right? So because of this, what is required is called an atomic operation. Right? So we want the update of these two variables to happen together atomically, right? So we don't want any other thread to be ever to see a state which is intermediate. So all threads either see x equals 1, y equals 2, or x equals 2, y equals 3. So there's no intermediate state that it ever sees at any point of time. That's what we sort of like want to provide, and this is called an atomic operation, right? And now if you think about it, like an atomic operation is surprisingly tricky to sort of like do, right? And one sort of like construct people use to do this is through locks, right? And the idea is that there's basically a lock on the code. So so you basically get a lock, and then after you get a lock, you modify x and y. So after you got on the lock, you modify x to 2 and to y to 3. Now this is being done by one thread, and another thread, let's say thread 2 wants to read x and y. Now what we could do is we could say x2 also needs to get the lock in order to see the values of x and y. And because like thread 1 is not done updating these values, thread 2 cannot actually read those values. So once thread T1 updates x and then updates y, what it will do is it will unlock the values, and then T2 gets a lock on those values, and then you can see, oh, x equals 2 and y equals 3, and then there's no problem. Right? So you basically want a mechanism by which you can say, while I'm updating this piece of code or like doing these instructions, nobody else can interfere, right? And this can take many different forms, right? For example, you could say no other thread can actually read x and y while I'm updating it, or you could say no other thread can update x and y while I'm updating it. So the basic concept here is called mutual exclusion, right? So both threads, while they're operating on x and y, because there is a lock, have exclude each other from reading and writing. And of course, the lock that I'm talking about is really the most basic coarse-grained kind of lock, where if one thread has a lock, another thread cannot even read it. Right? In actual code, these are much more fine-grained, and you can have reader locks, writer locks, and like all sorts of variants like that, right? But the basic idea is very simple. Whoever holds the lock is the guy who can do reads or writes. If you don't have the lock, you have to wait until somebody gives you the lock, right? So that's the basic idea behind mutual exclusion. Now, if you just do what I described, you will get very poor performance, right? Because like basically thread 2 is blocked until thread 1 finishes updating x and y. And if you think about the whole program as being reading or writing to x and y, even though you have 2 threads, only one thread will be active at any point of time. So you lose the parallelism, right? So you don't want to do this. So there are many different techniques as to how you can actually get good concurrency while still providing correctness properties. So you have things, for example, like read, copy, update, which actually allow you to do this. We don't actually like cover them in this course. These are sort of like a big topic in itself. But thankfully, Chris Rosbach and Calvin Lin at UT Austin have their own concurrency course as part of the online master's program. And if you're intrigued by this sort of stuff, I highly recommend that you take that course. So one other thing I will quickly touch on is the need for a hardware primitive to do this, right? So the hardware primitive is called compare and swap. So the idea, it's called CAS for short, and the idea is like really simple. So you say compare and swap x, and if it has value, let's say y, change it to value z, right? So what's an actual example? So compare and swap this variable I call my lock. If it is free, change it to locked, right? So that's really sort of like an example of like how you use compare and swap. And you know, like in actual programs, these would be replaced by, you know, like zeros and ones, for example. So you'd say compare and swap L, if it's 0, change it to 1, right? And the idea being you hold the lock if the value is 1. If the value is 0, it means that the lock is free and you can acquire it, right? Now the really interesting part here is if you don't have compare and swap, it's actually impossible to do it with just like normal read and write instructions. So let's actually sort of like look at that, right? So let's say the idea you want to do is you want to check, right? So the code you basically write is like if L equals 0, then L equals 1. It seems simple enough, right? Like this is basically what compare and swap was doing. But the real sort of like kicker here is that this is basically two operations. It's a read of L and then it's a write of L. It's not one hardware operation. So what could happen is this sort of like very interesting case, which I can show if my pen works. So you have thread 1 and then you have thread 2. So thread 1 executes if L equals 0, so it has read the value of L. It sees that, you know, like it's L is 0, so it's going to do L equals 1. So it's at L equals 0 at stage. Then let's say that the operating system sorts of like, you know, schedules out T1 and then schedules T2. T1 also checks L and then says it's L equals 0. Oh great, so it says L equals 1. So it is now set 1 and it will start updating X and Y. Let's say it's swapped out. And now T1 returns, it's already checked the value of L, so it's not going to check it again. So it then sets L equals 1 and then starts executing, changing X and Y. So you can see that when the read and write are separate instructions, even if you just did this check where if L is 0, like change it to 1, you will still get problematic behavior. For in this particular case, both T1 and T2 think they have the lock, even though it's supposed to, only one person is supposed to get it at one point of time. And the reason is because between read and write, your thread could be context switched. It could read an old value of L and then write a new value. So because of this, you really need one hardware primitive, right? So you need one instruction which does both reads and writes, and that is really compare and swap. So that's sort of like a nice little nuance as to why you needed compare and swap. As I mentioned before, for more details, if you're intrigued by this stuff, please take Chris and Calvin's concurrency class.